If we start with 2 dy by dx equals 5 minus 2y, then we want the y's on one side and the x's on the other. So we'll have the integral of 2 over 5 minus 2y dy equals the integral of 1 dx. You don't have to write the 1, but it makes it easier to see what the integral is. So, for the left-hand side, this is essentially an integral of the form 1 over y dy, which would give us log of y, plus a constant in the general case. So this is going to be log of 5 minus 2y. We have a constant of 2, but we also have to think if we differentiated log of 5 minus 2y, then the chain rule would give us a minus 2, so we have to divide by minus 2. And that gives us x on the other side, so the integral of 1 is x, and we do have to have a constant. We could have a constant both sides, but of course we could just subtract, so we only need a constant on one side. So we also have that when x equals 0, y equals 1, so we can substitute those in, see what we get. So of course those 2's cancel, so we have minus log 5 minus 2 equals c, and therefore c equals minus log 3. So we can put that back in, so that gives us minus log 5 minus 2y equals x minus log 3. Now we want to get it in the form y equals, so if we add the log 3 to the other side, then that gives log 3 minus log 5 minus 2y equals x. Then using the log rules we get log a minus log b equals log a over b. So we can now write log of 3 over 5 minus 2y equals x. And then we can do e to the power of both sides, and e to the power of log x is just x. So the left hand side just becomes 3 over 5 minus 2y, and the right hand side becomes e to the x. Now if we invert those, we get 5 minus 2y over 3 equals e to the minus x. 1 over e to the x is e to the minus x. So 5 minus 2y equals 3 e to the minus x. Subtract the 5 from both sides and times everything by minus 1 gives us 2y equals 5 minus 3 e to the minus x. And then finally y equals a half of 5 minus 3 e to the minus x. And we're done.
It's difficult to visualize differential equations and see what they look like. One way we can do this though is to have a look at the equation. So this is telling us what the gradient needs to be for values of y. So if we have y equals 0, then that would give us dy by dx is 5 over 2. So what we could do is put a gradient of 5 over 2 at various positions along the y equals 0 line. So just roughly that's sort of something like that. A bit better. Whoops. These aren't meant to be all the same. They're roughly going up 5 over 2. When y is 3 over 2, the gradient is 1. So 3/2 is 1.5. So here we've got more like that. And then when y is 5/2, dy by dx will be 0. So that's 2.5, so we're getting gradients like this. Now I'm going to change all of the colour of all of those for a reason you'll see in a minute. So we'll change them all to blue. Okay, so what that's telling us is that any solution to this, and there will be many solutions of course because it depends on the fixed point that we're given or some sort of condition. In this question of course we're told that it passes through the point 0, 1, so when x is 0, y is 1. But if we change that point we're going to change the curve. But what we can see is that probably we have something like this going on. Something like that, depending, as I say, which point it goes through. Now, it happens that in Geogebra there is a function or a way of doing that, and it's called a SlopeField. So I'll put that on now, and you can see that the blue gradients that I drew in, but I'll get rid of the text because we don't need to see that now. So the blue lines that I put in are about right, and then we can see here we're getting that, and then it's getting steeper. So now we'll get rid of those. But you can see that this line I've drawn does sort of follow through the gradients given for various values of y. So let's now have a look at the actual function, and what I'm going to do is put that on. So that's what it looks like, and that's when it's going through 0, 4. So if the given point had been 0, 4 in this question, that's what the curve would have looked like. And then we can drag this down and you'll see it change. So if we go down to 3, then it's still tailing off at 2.5 of course, because that's where we have a gradient of 0, and you can see that that's going to be the minimum value for the function. Now if we go down through 2.5, now it's flicking either side because that isn't exactly 2.5, but you can see what's happening. And then if we go down to the point we've been given, then that's what it will look like. And in fact Geogebra has another function called SolveODE, ordinary differential equation, and that brown line, which you'll be able to see when I slide the other one out of the way, has been generated by putting the actual question into SolveODE. That's given us that brown line there, which is the function y equals 1/2 brackets 5 minus 3e to the minus x. So Geogebra allows us to do that. So that's a really useful function within Geogebra called the SlopeField, and it allows us to get some sort of idea of what's happening with a differential equation.